All right, my friends, let's practice some domain, range, and asymptote questions, IB style. Here we go. Let's say you get a function, f of x is equal to 3 over x plus 5, and you're asked to figure out the domain, the range, and both the vertical and horizontal asymptotes. How the heck are we going to do that? We're going to cover it right now. First, let's look at the domain and the vertical asymptote. Since those are basically a pair, they go hand in hand with each other. If we look at this function, it's got an x in the denominator of a fraction. We know that we're not allowed to divide things by 0, so that's going to tell us something about the domain of the function. If we look at that x plus 5 component, we say, okay, well, there's one specific value that when x is equal to that number, that's going to give me a 0 in that denominator. Maybe you can see that when x is equal to negative 5 plus 5 gives you 0. That's off limits. So our x is not allowed to take on a negative 5 term. Other than that, though, everything else seems pretty fair game. So we can say that the x has a domain for all real numbers, except that x cannot be equal to negative 5. Otherwise, that fraction is going to break. That's it. That's the domain for this function. Nice and simple. And look at how beautiful this is going to be. Once you figure out the domain is, or maybe you're even given the domain, figuring out the vertical asymptote is easy because it's literally just going to be the equation to the line that's off limits for the x values. So in this case, since x is not allowed to be equal to negative 5, x is equal to negative 5 is the equation for our vertical asymptote. It's fair game, easy pickings. Now let's work on the range and the horizontal asymptote, since those two are also a nice pair that work with each other. The way I like to do this is I'm going to rewrite this fraction, but in a bit of a weird, different way. So maybe that helps us see what's happening. I'm going to rewrite this function, f of x, is equal to 3 over just the word something. And I'm writing something because there's an x variable in the denominator, right? And when the x variable is in that denominator, it can fluctuate from big numbers, small numbers. It can just take on different values. That's what a variable does. And the question we're going to be asking ourselves is, what happens when x gets really, really big, or that something in the bottom gets really, really big, or really, really, really small? When this something gets really, really big, if you take a number and divide it by something huge, well, you're going to be dividing it up into really, really small pieces, maybe like infinitely small pieces, but it's never going to quite be equal to 0. You're never going to have nothing, right? You're always going to have something really, really small. That tells us that this number is eventually going to approach 0, but it's never going to quite be equal to 0. That's going to be really important. I'm going to box that fact. Let's think about what happens when that something gets really, really small. Well, when you take a number, in this case 3, and divide it by something really small, or smaller and smaller components, you're eventually going to get bigger and bigger pieces out of it, right? If you're dividing one pizza up between 100 people, okay, well, everyone's going to get a pretty small slice. But if you divide that same pizza up to 10 people, or 5 people, or 2 people, all of a sudden you end up with like a half a pizza, a lot more pizza. If you do this over and over and over again with really small numbers, eventually that y value, that pizza slice, is going to get super infinitely big, but never going to quite touch infinity because it couldn't. That's like a weird an abstract concept. What we end up with then, if we look at these two things together, is that the y values for this function, or the range, is going to be everything in between those two numbers. So in other words, y, in this case the range, can take on any real number, except what we're seeing earlier is that, well, the y is never going to quite be equal to 0. And the reason why is because, well, you're never going to have 0 pieces of pizza or 0 slices of pizza coming out of that division. So just like with our domain, we have one value that's kind of off limits. It's never going to actually happen the way that the function looks. Otherwise, everything else is fair game. And just like when we figure out the domain and the vertical asymptote go hand in hand, same thing with the range and horizontal asymptote. As soon as you figure out the range, super easy, the equation for our horizontal asymptote is always just going to be basically equal to the opposite of that range. So in this case, the equation for the horizontal asymptote is y is equal to 0. First problem, checkmate. All right, problem number 2. Let's say we're given this other function. F of x is equal to 3x over x cubed minus 1. Slightly trickier, but nothing we can't handle, folks. Let's look at the domain and the vertical asymptotes again, because that's going to be the most helpful way for us to start these problems off. Looking at the bottom of that fraction again, we ask ourselves, are there any forbidden values, any values that are going to make that fraction equal, or the bottom of that fraction equal to 0? Looking at it, we can see, well, when x cubed, what number cubed is going to give me something that's subtracted by 1 equals 0? If I can rewrite this if you want to look at it more algebraically. If we want to try to set that denominator equal to 0, because that's going to be able to tell us what those off-limits numbers are. Well, if you look at that, I can add 1 to both sides of this equation. So x cubed is equal to 1. And the only way that a cube is equal to 1 is when, well, x is equal to 1. 1 times 1 times 1 gives me 1. Notice that if this is a square number, you have the positives and negatives issue, because if you square a negative number, it becomes positive. But in this case, because this cubic is odd, then the signs are always alternating. So in this case, only x is equal to 1 is a solution to that problem. That means that when x is equal to 1, that's going to be off limits. No bueno. So the domain for this, just like we did earlier, is x is all real numbers, except such that x does not equal to 1. Boom. Domain checkmate. And if we again go back here and look at the vertical asymptote, maybe you remember from the previous problem that as soon as we get the domain, the equation for the vertical asymptote is literally just the equation for the x value that is off limits for that particular function, which is going to be equal to x is equal to 1. Let's switch it up. Domain. Now we do range. I'm going to rewrite this function now. 3x over x cubed minus 1. Now something funky is happening here. In the previous problem, we said, well, we could just rewrite this as a constant 3 over something and play around with that variable. But in this case, it's a little trickier because we've got a variable on the top and a variable on the bottom. So as x is getting really big, we're getting really big numbers on top and also really big numbers on the bottom of this fraction. That's going to be a bit of a problem, but nothing we can't handle. Instead, for these ones, if you've got a function in where you've got an x component on the top and bottom, the best thing or the easiest thing we're going to do is we're going to look at the powers. What power is bigger? Is the power of x bigger on the top or on the bottom? If the power of x is bigger on the bottom, like it is in this case, the bottom part of this fraction is going to be increasing at a way, way, way faster rate than the top is, which makes sense, right? If you're having like x versus x cubed, the x cubed is growing way faster because it's going at x 3 times the speed than the x component. So what that means is if we rewrite this as those somethings, right? 3 somethings over, I'm going to write this really big, something cubed. It's weird math notation. It's not really math notation, it's Arthur notation, but it works. If we rewrite it like this, as x is starting to get really, really big, well, the bottom is going to start, or the top is going to start getting big, but the bottom is going to start getting way, way, way bigger, which means that that bottom is always, always, always going to be bigger than the top for big values of x. So as x gets really big, this guy is going to approximate or go towards 0, just like in the previous case. It's never going to quite get there, but it's going to go towards the 0. Nice. So just like we figured out earlier, because that value is approaching 0 for really big values of x, we can say that the range for this function is all real values of y, except such that y does not equal to 0. And because we've already figured that out, we can come up here and say the horizontal asymptote then is therefore y is equal to 0. Because again, it's just the equation or the y value at the point where the range doesn't exist or the y values don't exist for that function. That's it. Easy peasy, problem number 2 in the bag.